Now we're talking about inside of a molecule, those different forces, okay? So a chemical bond in general is the attractive force between two molecules. The reason why atoms bond in the first place is for stability, okay? If it didn't make them more stable, they wouldn't bond in the first place, okay? So just be aware of that. That's why, which of our elements never bond with each other?
The noble gases.
The noble gases, right? They don't bond because they're already stable. And that's another way you can predict, are these two going to bond with each other? Well, if they bond and they don't make each other stable, then they don't bond in the first place, right? So, don't say it out loud, but show me on your fingers how many valence electrons make something stable. Show me on your fingers, how many electrons do they want to be stable?
Oh.
Good, yes. There's a lot of different ways of showing it, but the answer is 8, right? And then the rare case of 2, right, with hydrogen, right? I guess a trick question there, okay? So the whole goal of all of our atoms is to get 8 valence electrons or a full octet. So what we're going to talk about for the rest of the day are the 3 different ways an atom can do that, okay? So our first option is atoms can gain electrons, right? If I only have 6, I gain 2 more, I now have 8. Keep in mind that when something gains electrons, their charge is negative. Okay, so be cautious with that, because remember, gaining electrons makes them negative. We call that an anion. The other way in which they can do it is they can lose electrons, and that makes a cation, which is positive. So they can gain to get happy, they can lose to get happy, or final option is they could share, right? Is they can share their electrons to get 8. So 3 different ways in which an atom can achieve that stable full shell. Okay? So our first type of bond is an ionic bond. In an ionic bonds are a transfer of electrons. Okay? Transfer of electrons is what makes something an ionic bond. Okay, so imagine this with me here, right? I have a sodium atom. Everyone look at this picture with me real quick, okay? This sodium atom has 1 little valence electron. How does sodium get stable by giving its 1 away?
Because it has 8 in the outer shell.
Yeah, because in the inner shell, has 8, right? So if I get rid of that 1, all right, now I have 8. Chlorine has 7 on the outside, so they're a perfect match. Sodium gives it away, chlorine's happy, sodium's happy. Now why do they even stay bonded though? Why doesn't sodium just give its electron away and then peace out? And it is what keeps the atom together? Austin?
Because they have different charges and they connect to each other.
Yeah, so when sodium gives its electron away, it becomes positive, chlorine becomes negative, and opposites attract. Right? So this is a relationship of opposites. The positive and negatives are held together by that attractive force. What's interesting is we have this 3-step process. Okay? The first step is the electrons are transferred. Someone has to give them away, and that's always the metal. Another one has to accept it, and that's always a non-metal. Why wouldn't it be the other way around? Why wouldn't non-metals ever give up their electrons?
Because they're stronger.
Yeah, they're high electronegativity. They hold on to them tightly. You can also think simply, right? They're already on the side of, hey, I have 7. Why am I going to give any of mine away when I'm just 1 away from it? Metals have very low electronegativity, so they're willing to give it away. Okay? Those electrons are transferred. The ions are then formed, and then the opposites attract. 3-step process of making an ionic bond. Okay?
Does that make sense?
Yeah.
Okay? So one thing that's unique with ionic bonds is that even though it's like Bailey gives to Elise, right? Bailey gives her electrons away to Elise and Elise takes them. What we get is this giant network of a solid. Because what you end up with is a whole bunch of positive, negative, positive, negative, positive, negative, and all positive and negatives are attracted to each other. This is also often called a crystal lattice. Okay, so that's why we call them ionic crystals. The other thing is because it's this like giant network of a ladder, or that's like another way of looking at it, this is why we call it an ionic crystal. So the tricky thing with an ionic crystal is that there's one sodium atom, so sodium is the yellow. Even though the transfer technically happens between just one sodium to one chlorine, that one sodium atom is surrounded by how many chlorines? Think of like a sodium in the middle of the crystal. Yeah, it would actually have 6 different chlorines all surrounding it. Which is why with ionics, their formulas are always considered empirical. We don't know how many of each we have, but we do know the ratio. We know that the ratio in particular for like salt is NaCl. For every 1 Na, I have 1 Cl. But the formula could be like Na200, Cl200. But we always write the simple empirical form. That's what it means by empirical, is that we reduce the numbers down. But that's unique to ionic substances. Okay? All right, so we have ionic, which is where they are transferred. Okay? Our next type of bond is covalent. Okay? So covalent is the sharing of electrons between 2 things that have high electronegativities. So neither of them want to give it up, so they both share with each other instead. Okay, so the sharing of electrons between atoms with high electronegativities. Once again, the goal, even though they're sharing, is to always get 8. Okay, the goal is to always get 8 valence electrons. So they're going to share in such a way to get that 8. So with covalent, we've talked about how sometimes they share, but it's not equal. Anyone remember what that's called? Somebody said it. Polar, right? So polarity is that relationship of where they're shared but not equal. So here's kind of the 3 extremes. Okay, non-polar is equal sharing. Okay, the electrons are shared equal. Polar, they're still shared, but it's not equal. And then, is ionic sharing? No. Ionic is a complete transfer. Somebody won the tug of war or somebody gave up. And they just all go one way. So we said in the warm-up today that when a nonmetal goes with a nonmetal, it's covalent. A metal with a nonmetal is ionic. Okay, and that's not a bad way to do it. What I'm going to show you right now is a little bit more like mathematical, scientific way of doing it. Very similar, but we're going to use what's known as electronegativity values. So by taking the difference in electronegativities, you can know for sure what type of bond would form. In a sense, you could think of it as, okay, these 2 atoms are having a tug of war. We're going to compare their strengths to see what the end result is. Right? Is it going to be equal, unequal, or complete transfer of electrons? Okay? The breakdown is for covalent, it's greater than a 1.7 difference. And ionic is, I said greater, huh? I meant less than. Sorry, covalent is less than 1.7. Ionic is greater than or equal to 1.7. Okay, or another way you can think of it, go back up to this picture in your notes. Everyone see that picture? And draw an arrow underneath. Okay, so draw an arrow underneath. So here's kind of our different sections, okay? So if you have something that is from 0 to 0.4, it means it's non-polar covalent. Okay? And then from 0.4 to that 1.7, we get polar covalent, and then anything above 1.7 is ionic. Okay? Okay, so back up front up here, everybody, so look at your little chart I gave you. Right on. Nice. Okay, so on your assignment that we'll work on here in just 1 second, you're going to see a question very similar to this. So this isn't in your notes, but I just want to show you kind of how to walk through it so when you get to that, you know what to do. Okay? So what you're going to do is you're going to compare two different elements. So look at your electronegativity chart I passed out and find calcium. What is the electronegativity value for calcium? 1. And then what is it for chlorine?
3.1.
3.1. So you always take the bigger minus the smaller. So we're going to do 3.1 minus 1. Okay. So we just looked at the chart and got our values. This isn't on your notes again, for those that are still searching. Okay. So then Mitch, everyone listen to this. How do you know it's ionic?
Because it's greater than 1.7.
Yeah, so then you go to that arrow we just drew in. Anything greater than 1.7 means it's ionic.
Oh.
How would I know if it's polar covalent?
It
It's less than 0.1.
So then it's between
Point
0.4 and 1.7. And then anything less would be nonpolar. So all you do, the math is quite simple. You just divide the bigger minus the smaller.
Subtract.
And then compare the value at the end.
Are we
We
done
have
taking
this on our
notes then?
test.
Is this our
Okay? No, we have a few more to do.
This
But I just want to show you how to do
the
that.
easiest thing we've done all year.
Oh, good. Yeah, it's not too hard once you know what you're
Do
doing.
we have this on our test?
Yeah, and if I ask you these questions, I'll give you the values.
Okay.
Yeah, I don't expect you to memorize electronegativity values. Tell me this, from the warm-up,
Oh, I guess you could kind of
you could estimate it from what we did, right? But knowing between polar and non-polar is where you have to have the numbers for, really. Right, to know that difference.
Yeah, because you can get ionic or...
Ionic or covalent you should be able to figure out, but then to differentiate between the two.
You're right,
Okay, so with covalent bonding, it's about the molecules now. So it's not a big network. It's just down to the molecules, okay? So with covalent bonding, a covalent formula we don't simplify, okay? Glucose is C6H12O6. We don't simplify that down, we keep the total number, okay? C6H12O6 is not the same thing as CH2O. Okay, that's not sugar anymore. I don't even know what it is, but it's not sugar. I know that much, right? So with ionics, we simplify the formula to the ratio. Covalents, we do not, okay? We write the total. Okay, so the key thing that's different with covalents is that when I separate them, once again, we're not separating the bond, we're separating the intermolecular forces, those IMFs. Okay? Just like we talked about when I boil water, it's that these are separating from each other, not the bond itself. Okay? Versus if I tried to boil salt, you're actually having to start breaking apart the forces. Okay? All right, our last type of bond that we need to talk about is metallic bonding. Okay? So metallic bonding is kind of a combination of both. It's a little bit of a transfer and a little bit of a sharing. I think of it as a sea of electrons. Or another analogy that I think of is metallic bonding is sharing, but covalent would be like Topher shares with Peyton and Peyton shares with Topher. That's covalent. They're sharing with each other. Metallic is like communism, because we're all going to share with everyone. Okay, basically we're going to dump all our electrons into the sea and we all share with each other. Okay, rather than just sharing with one other person. So here's kind of how it looks. These little blue ones would be like our metals. The red ones are their electrons. So what they do is they just all throw their electrons in the middle and the electrons just flow everywhere. And we get this sea of electrons. Why couldn't, let's think about this real quick. So if I have sodium, how many valence electrons, let's do another smiley face, we haven't done one in a little bit. Show me on your fingers, how many valence electrons does sodium have?
I guess.
Keep it close to your body for me. How many valence electrons does sodium have? And how do I know it's one?
Because
It's in the very first column, right? Column are valence electrons, okay? So sodium has 1. So if sodium wants to bond with itself, if it's a metal, why can't it just share with one other atom to be happy?
Because that's only two.
that's only 2's got
1
8.
plus 1 does not equal 8.
Well, unless you're hydrogen.
So the reason why we get this sea of electrons is because they don't have enough to just share with one other. So they kind of do this big group sharing in order to get their full octet. Okay? So with this, the electrons are first released. That's the first step in metallic bonding. Then, because those electrons are released, we end up with positive and negatives, cations, and then the electron C, and then the opposite charge is what attracts them together. Because you have the positive metal ions and all of the negative C holds the metal together. Okay, so that's what holds a metallic bond together. The cool thing about metals in general, or actually any chemical bond, is the bond itself helps describe the properties, right? Like we talked about with ionics, one of the reasons why they're brittle is that because you can force the charges to repel. With metals, this is why we end up with malleability, right? So what is malleability again?
How you can shape it.
Shaping it, right? This is where like it can dent. If you hit it with a hammer, you can make it into different shapes. Metals are malleable because of this flowing sea of electrons. It also what allows them to be what's known as ductile, which is the fancy name for making them into a wire, right? That is unique. You can't make salt into a wire. Doesn't really work out that way because the way it's bonded. This is also why metals are shiny, or like we said, lustrous. Okay, so luster is the shine. It's also why metals are very good conductors, because electricity is the flow of electrons. So if metals are a sea of electrons, electricity can flow through them quite well. Same thing with heat. Metals are very good thermal conductors. They conduct heat very well, right?